Hello and welcome to a presentation of operational design, advantages and disadvantages, and global market effects of pressurized light water small modular reactors. My name is Christopher Haney, and I'll be presenting this project on behalf of myself and Robert Barnes for our Thomas Edison NUC-495 Capstone project. The topics we'll be covering with today's presentation are basic operation, with a specific look at the NuScale power module, which is the closest to production, major differences in design against other small modular reactors, global experience, safety characteristics, material proliferation, and advantages, specifically the EPA requirements, design advantages, power production, and facility footprint. We will also be discussing disadvantages, specifically loss of economies of scale and manning, economic feasibility of this technology, and at the end we will finish the presentation with a summary and general conclusions we've drawn from our evaluation. So why, oh why, are we discussing this? Well, in 2012 alone, the global economy used 8,979 million tons of oil equivalent energy. This is approximately equal to 376 million terajoules of energy, or the detonation of 6,000 of the largest nuclear warheads ever tested by the United States. This immense amount of frivolous consumption is only getting larger as nations invest in technology-driven economies rather than depending on the physical work of their constituents. For the moment, the world depends on an energy market predominantly supported by quickly retreating fossil fuel reserves to feed its energy cravings. The global economy is in need of dependable energy. It requires minimal startup capital, efficient manufacturing options, and safe operations processes. The energy market today has many options available, all of them with their own critical fail points. If we intend to continue to have large amounts of reliable, clean, and efficient sources of power, we will need to understand and pursue the new technologies available in the nuclear energy field. We will be analyzing the overall operational design, advantages and disadvantages, and global market effects of the pressurized light water small modular reactors to evaluate the technology's potential implementation. First, let's cover just a little bit of history to understand why we're covering the light water option. So following the physics discoveries of fission, moderation, and nuclear chain reactions, early experiments began to show that uranium could provide a sustained fission reaction using graphite or heavy water as a moderator. However, in May of 1944, the Lobel reactor at Los Alamos was the first reactor to bring uranium to criticality. Although this would not be strictly considered the first light water reactor, it was the first aqueous homogeneous reactor and the first reactor to use ordinary water as its moderator. Utilizing information from this experimental reactor, the U.S. government not only continued production of the atomic bomb, but the discovery was then pushed towards energy-producing technology. In the early 1950s, the first nuclear submarine was built, the USS Nautilus, whose reactor depended on light water as its moderator. The successful use of light water reactor technology with the military spurred light water technological proliferation and has continued to be used for some 60 years as the basic reactor design for nuclear submarines. So due to its long availability and rather cheap production costs, light water reactors have become the most common type of nuclear reactor in the world. There are currently 359 reactors in operation, including those temporarily shut down in Japan, 27 reactors under construction, and 27 countries that are currently using the technology. The current global fleet of light water reactors has a power generating capacity of over 320 gigawatts, and there's no sign of slowing down production. This dense international use of light water reactors has provided the field with many years of operational testing and research data from multiple perspectives that continues to make this reactor option safe and economical. So one of the main reasons for evaluating the pressurized water small modular reactor technology is the key operational characteristics being pushed into their design. Pressurized light water reactors are the current primary reactor type used for electrical generation, and multiple options of light water modular reactors are in the design and approval process, including the Babcock's and Wilcox in-power reactor, the Holtec inherently safe modular underground reactor, or HISMR 160, the Westinghouse SMR, and the NuScale power module. However, details entailing technical specifications used for light water reactor examples will be specific to the NuScale power module, the product supporting the most advanced concepts and currently nearest operational use in nuclear first-of-a-kind activities. The fuel organization of this module, for example, is a reduced height 17 by 17 standard light water reactor fuel assembly. Each assembly consists of 264 fuel thimbles maintaining fuel pellet material made of uranium oxide held in a zircaloy-4 cladding and enriched to 2.5 to 5% by weight. The fuel is maintained in power modules that can be connected according to maximum power requirements. The current full-scale design maintains 12 modules connected together, with each providing 45 megawatts of electrical power for a total capacity of 540 megawatts per plant. The modular design of the reactors and the options allowed by this design are the primary features making this technology an attractive investment. Also, by utilizing an oxide, a pure metal as a fuel material, allows for a much greater melting point, and since this material is already oxidized, it also will not burn. These attributes allow for the fuel material to experience more extreme transients in higher thermal environments without causing core damage. The fuel is additionally maintained in pellet form to provide a greater thermal conductivity and a more even fuel burnout, increasing efficiency and core life. The lower enrichment fuel, used within a light water reactor environment, is sufficient for producing energy while maintaining a lower probability of radiation hazards and release of fission material during an accident. The control rod drive mechanisms, or CRDMs, used in the NuScale power module are provided by EMD of Curtiss-Wright. EMD has been manufacturing and designing CRDMs for over 45 years and currently has 5,000 CRDMs operating in 88 plants worldwide. The models being used in the power module provide precise power control with a qualified life of 7 million step changes. These CRDMs are organized into 16 control rod clusters broken into 2 controlling groups situated to provide greatest control and minimal power peaking. The long-standing availability and use of these standardized CRDMs provides the power module with readily available and lower-cost primary components, allowing for an overall lower price tag for manufacturing and maintenance of these units. Utilizing prior tested and operated designs also adds to the margin of operational safety for this newly devised reactor layout. The enclosure for each of the NuScale power modules measures 65 feet tall and 9 feet in diameter. The enclosure includes a fully integrated reactor pressure vessel, steam generator, pressurizer, and containment, which allows for the entire containment reactor vessel module to be sent to any destination in segments for prompt installation. Each module is designed to operate on a 4-year refueling cycle, but due to limitations set by the Nuclear Regulatory Commission, or NRC, inspection criteria, they are limited to operate on a 24-month cycle. A plant with a full complement of 12 modules will have a scheduled outage for refueling every 2 months. The entire vessel and containment is maintained in a pool of water that is located below ground level. And establishing reactor coolant flow through these vessels depends on a heat differential, and therefore a density differential, and gravity to produce natural circulation flow. As control rods are withdrawn, the nuclear fuel fission process is accelerated, causing a large amount of heat. The heated reactor coolant near the fuel then moves up through and over a tube called the riser section, which has steam generator tubing surrounding it. The steam generator water removes heat from the primary coolant, which then becomes more dense. This denser liquid is forced back to the bottom by gravity, and the fluid head developed by the rising heated primary coolant. The cooler liquid is then reheated by the fission process, and the flow continues. The flow of the heated steam generator water, or secondary coolant, is directed to a pair of steam-driven turbine generators. This generator will utilize the energy stored in the steam to develop work within the turbine, then direct the exhausted steam to a condenser. The subcooled liquid is directed to the suction of a feed pump that forces the liquid back to the steam generator, recirculating through the secondary flow process. The pressurized water used in the description of this reactor type refers to the material used as the moderator. The moderator is purified and chemically treated light water that is utilized as a cooling medium, a heat transfer agent, and the fission process moderator. These characteristics make it an exceptionally functional and expensive means of operating with nuclear power. Light water has a very strong ability to absorb heat. The specific heat capacity of liquid water at ambient pressure and temperature is approximately 4.186. This means it takes about 4.2 joules of energy to raise 1 gram of water by 1 degree Celsius. The specific heat capacity of liquid water per gram is higher than any other common substance other than pure hydrogen gas, which has a specific heat capacity of 14.3. Hydrogen, however, comes with the inherent characteristic of it being explosive when mixed with air in greater than 4% and less than 75%, making water the safer option for cooling reactor systems. Under steady-state conditions, liquid water has a low ability to conduct heat. The thermal conductivity of liquid water is low at 0.58, when compared to the high value of liquid sodium at 86. Liquid sodium is used in some fast breeder reactor designs and as a thermal storage medium in many solar plants for its heat capacity and thermal conducting characteristics. However, liquid sodium does not work well as a moderator, which is the third reason water is used for this reactor type. Now, the primary use and reason for using light water as a moderator is water's ability to moderate or slow down neutrons. When considering materials for use as moderators, 2 characteristics need to be evaluated: the material's macroscopic cross-section for absorption and scattering. The 2 materials providing the lowest value of necessary collisions to reach thermal energies are light and heavy water. Both of these compounds contain hydrogen, which due to its high macroscopic cross-section for scattering at 82 barns, collide with fast neutrons efficiently. The added hydrogen atom in the deuterium compound makes heavy water about 80 times more efficient at moderating than light water. However, creating and utilizing heavy water comes at the heavy expense of approximately 4,300 American dollars per kilogram. The light water SMR designs are all based on concepts currently used in many commercial and military pressurized light water reactors. The major design difference, which has caused these reactors to stand out from the current global fleet and become a popular economic and energy discussion, are their much smaller thermal outputs and modular production and installation concepts. The size of these SMRs ranges from 45 megawatts of the NUC-scale power module, which can include up to 24 modules in one facility, to the 200 megawatt reactor design from Westinghouse. The light water SMRs are also competing against fast reactor and high-temperature gas-cooled SMR reactor designs. The smallest of the complete SMR options comes as small as 25 megawatts, as available in the Integrim Molten Salt Reactor 25 model from the Terrestrial Energy, and the largest is the Prism from GE Hitachi, providing 311 megawatts output per unit. Both of these reactor options are fast neutron reactors that can utilize light water SMR fuel waste, and will be discussed further in the advantages and disadvantages section. Now, as far as safety, the designers of today's light water reactors are focusing on the engineering concept of inherent safety features. By definition, inherent is to be existing in someone or something as a natural and inseparable quality. So when applied to reactor safety features, this means that the system's characteristics are built into the core design and not added on to provide their function. By building safety into the basic design, many hazards are eliminated or minimized rather than controlled. This philosophy and way of thinking has the added potential of making the overall design simpler, safer, and cheaper. Some inherent safety features are seen within the light water SMR designs are the use of light water, utilizing natural circulation, maintaining the cores below ground level, and placing the cores within a pool of water, and the smaller size of SMRs. This inherent safety design is also supported by the passive safety features, which are called so because they do not require operator action or electronic feedback to be initiated and to safely shut down a reactor in the event of a specific casualty. These features depend on laws of physics to slow down or stop the nuclear fission process. The evaluation rating as to degree of safety as provided by passive safety systems is maintained by the International Atomic Energy Agency, or IAEA. This grading ranges from A to D depending on how many of the following the system makes use of: the no moving working fluid, no moving mechanical parts, no signal inputs of intelligence, and no external power input. An example for the light water SMRs is the cladding around the fuel pellets used in the core. Since a safety feature meets all the listed attributes, it falls under category A. A system or feature requiring all but one of the features for a light water SMR would be the scram function, which would be a category D. Now, these passive safety systems are used as the primary measurement for emergency response timing and casualty design, assuming failed or incorrect operator action. By doing this, many old-style active safety systems are either no longer required, such as loop-installed and pump-driven emergency cooling systems, or are only installed to meet legal requirements, such as borated solution injection systems. Now, combined, the passive systems of today's pressurized light water reactors provides a new level of safety never experienced in the nuclear field. The NUC-scale power module, for example, operates all of its passive safety systems without pumps, AC or DC power, or addition of water. This design provides passive cooling of the reactor for 30 days, followed by an unlimited period of cooling to air. Overall, the reactor prevents the core from becoming uncovered during any design basis accident and provides 7 levels of protection, 4 more than any conventional reactor. As per the Treaty on the Non-Proliferation of Nuclear Weapons, nuclear proliferation is the spread of nuclear weapons, fissionable material, and weapons applicable to nuclear technology and information to nations not recognized as nuclear weapon states. The steps within the fuel life with the highest risk for proliferation are fuel enrichment, fuel manufacturing, during operation, and during storage or recycling. Now, pressurized light water SMRs are not inherently more resistant to proliferation than conventional pressurized light water reactors, with the exception that an SMR could contain less nuclear material when the rated power output of the core is less than that of its conventional counterpart. Now, most SMRs are to be built below grade, which provides safety and security improvements. This characteristic addresses weaknesses to both natural disasters and sabotage scenarios. However, the most significant non-proliferation advantage of SMRs is more logistical in nature than technological. By centralizing the production and retirement process, the ability to access nuclear material is significantly reduced. This spoke hub distribution model will require fewer movements of radioactive material, and when moved between the production facility and power plant, the material is already sealed within a reactor vessel, thus minimizing potential for receipt by an outside entity. The necessary step when analyzing use of energy production technologies for long-term viability is evaluating the environmental effect of the production process. Now, currently, coal provides approximately 41% of the world's electricity needs, making it the primary source of electrical power generation and primary competitor to nuclear energy. The majority dependence and growth of need is primarily due to expansion of developing countries, which do not retain a funding, legal privilege for the MPT or technology required for nuclear-dependent energy. However, countries like the U.S. are taking a stand against the use of old polluting coal technologies. The EPA administrator said at a 2014 conference that the high cost of climate inaction are affecting American children and families today, and it is important to limit carbon pollution. With this statement, the EPA proposed a rule that is intended to reduce carbon dioxide emissions from existing coal plants by as much as 30% compared to the 2005 values by 2030. This ruling, in combination with the mercury and toxic standards and the cross-state air pollution rule, will cause a loss of approximately 72 gigawatts of coal-powered electrical generation due to the shutdowns of coal plants as the field takes action to meet EPA requirements. This is enough capacity to reliably power 44.7 million homes, or every home west of the Mississippi with the exception of Texas. Now, maintaining approximately 27% of the electrical power production in the U.S., the natural gas industry has also been impacted by EPA restrictions. Electrical generation from natural gas produces about 40% less carbon than coal for the same amount of energy, yet many of the plants must be upgraded to meet the EPA emission requirements. However, the average age of natural gas plants is significantly lower than coal, and the adjustments required to meet EPA standards is more cost-effective for gas. The gas industry is standing by to take over the market left behind by coal, but the new requirements for fracking may prevent this. Now, fracking involves injecting pressurized liquids into underground formations to extract oil and gas that is normally inaccessible by conventional means. This method is a fiercely debated topic due to the environmental effects, but the technique has helped to make the U.S. the world's #1 producer of natural gas. However, on March 20th, the Obama administration imposed tighter restrictions on oil and gas fracking operations on public lands in an attempt to reduce the risk of contaminating water sources. These restrictions will apply to oil and gas drilling on federal lands, which accounts for 25% of the current fossil fuel output, with a focus on well-designed standards and pond and holding tanks. The expected increase in operating costs, updates, and design changes may slow or halt the natural gas boom and prevent gas from moving into the markets once held by coal. Now, all of this said, the nuclear field as a whole has been completely unaffected by the EPA restrictions. Nuclear energy plants do not produce criteria pollutants or greenhouse gases during the process of electrical generation. However, the process of building the facilities and developing and processing fuel do. The nuclear power life cycle emissions include products associated with construction of plants, mining and processing the fuel, removal and disposal of used fuel and waste byproducts, and decommissioning. Many studies have demonstrated that nuclear energy's emissions are comparable to green forms of electrical generation, such as hydro generation and wind, and are much lower than emission levels of coal and natural gas power plants. For example, the Department of Energy's National Renewable Energy Laboratory stated in their 2012 analysis of life cycle emissions that collectively, life cycle assessment literature shows that nuclear power is similar to other renewables and much lower than fossil fuel in total life cycle greenhouse gas emissions. This makes nuclear the most environmentally friendly and sustainable power option amongst the primary competitive source options. The argument for SMR technology is only strengthened when evaluating the design limitations of competing technologies. The primary fallback of wind and solar options are their inability to store energy. Both of these technologies are intermittent resources depending on nature to provide their motivators. Therefore, neither can meet base load energy demand without the use of storage devices. Energy storage devices, such as batteries and pumped hydro, are expensive to produce and maintain and add to the emission and waste footprint of these energy options. The inability of these renewable technologies to maintain a constant output also prevents supplying for peak load. When need is placed on the grid, a readily available source of power must be online for immediate consumption. Availability depends completely on environmental conditions an independent variable that will always plague these options. This characteristic forces solar and wind to play a supporting role behind 24-hour available sources such as nuclear. Another disadvantage of competing technologies are their location requirements. Solar, wind, geothermal, and hydropowered sources must all be located such that their sources are immediately and continuously available. This severely limits available options for generator locations and distribution hubs, restricting a community's decision as to which energy source to support. Dense installation of these technologies in a region can significantly drop overall energy costs, but this can also make supporting units necessary for meeting peak demand non-competitive, potentially increasing costs in order to maintain the grid support. Coal and natural gas plants need to be located near a primary source or have extensive support to provide continuous fueling. This is necessary due to the low electrical production value of coal and natural gas. For example, it takes about 1.05 pounds of coal to produce just 1 kilowatt hour of electrical power, and 1,000 cubic feet of natural gas to do the same. This means that the typical 500 megawatt coal and natural gas-fired plants use about 1.4 million tons of coal and 43,800,000 MMBTUs of natural gas per year, respectively. To an advantage, pressurized light water SMRs are not affected by any of these limiting factors. Pressurized light water SMRs are maintained in a sealed environment and may have all systems required for operation maintained within a closed facility. This electrical generation source can maintain a consistent and stable output despite changing environmental conditions. Also, since the design is independent of external conditions, the output can be utilized to support all grid conditions to include peak need. The added benefit of the modular design of these reactors is they can be scaled to provide the most efficient fit for fluctuating grids. This scalability and independence allows for the reactors to be installed in an environment type and in any environment type and support isolated communities or facilities. Along with these characteristics, these reactors utilize a source with an extremely high power density, which can support operations of a typical 500 megawatt reactor for 1 year using only 15 tons of uranium. This provides for required refueling timeframes that are in the years, such that minimal supporting external infrastructure is required, and the reactors can be located significant distances from sources. The overall design of pressurized light water SMRs makes their usability far superior to the other competing technologies. The loss of economies of scale is the single largest hurdle that must be overcome in order for small modular reactor implementation to become reality. Much of the benefit of SMR implementation centers on the ability to essentially fabricate and assemble the nuclear steam supply system. In theory, this would allow for advantages to be taken in the manufacturing, assembly, and quality assurance practices. In order for the deficiencies in the economies of scale to be overcome, the advantages associated with mass production must be more pronounced. However, the efficiencies gained by mass production are not instantaneous, as factory production needs to be optimized and organizational learning needs to be incorporated. Only once the production process is fully mature will the economy of mass production begin to offset the loss of economies of scale. In fact, Westinghouse estimates that the diseconomy of a small size would make the cost per megawatt about 75% higher than the cost of a large reactor. As some SMRs designed to operate on new technology, there's a need for substantial upfront capital expenditure in order to begin the manufacturing process. Westinghouse claims that it would need to book orders of 30 to 50 reactors at a cost well over $36 billion for design and production lines in order to cover its costs. This would be a largely prohibitive sum for a company that's still smarting from having zero orders placed for its AP600 power plant. Now, manufacturing process aside, there are other factors that contribute to a loss of economy of scale. One such factor is the annual fee due to the NRC for each operating commercial reactor. At present, annual fees requires that each operating reactor pay $5,223,000 as an annual fee. For a new-scale plant with a full complement of reactors, this sum would be $62,676,000, or roughly $110,000 per megawatt annually, compared to a typical dual-unit site's fee of $10,446,000, or roughly $4,300 per megawatt. This is a tremendous obstacle for the ability for SMRs to be cost-effective. Of course, there have been preliminary discussions about changing this fee structure. However, as of this writing, there's currently no reduction in fees relating total plant thermal output to the number of operating reactors. While the plan suggested by the American Nuclear American Nuclear Society would address this issue. An independent study by the US NRC has suggested that there is no correlation between a plant's electric output and the amount of work the on-site resident inspector must perform, suggesting there may be some reluctance on the part of the U.S. government to alter its current fee structure. Another significant barrier to SMR implementation is the Price-Anderson Act of 1957, which was enacted to ensure the nuclear industry against liability claims resulting from nuclear accidents. As the law is currently written, plants with a capacity greater than 100 megawatts are currently required to obtain and maintain $375 million in primary financial insurance, plus an additional amount known as secondary insurance, which is payable if there is a claim filed. Just as in the case of the current NRC fee requirements, this legislation puts undue burden on the SMR, as a new scale model would result in an exorbitant insurance payment even though its plants have a smaller source term and smaller megawatt output as the current generation of licensed reactors. At present also, the U.S. Nuclear Regulatory Commission places strict rules on the minimum manning for a power-generating reactor. The Code of Federal Regulations, which outlines the conditions for nuclear licensing, currently requires one senior reactor operator and one or two reactor operators per operating plant. This means that for a facility with a full complement of NuScale reactors, which is 12, they would need to have 12 senior reactor operators and 12 to 24 reactor operators per shift. Extrapolated out to cover the standard 5-crew, 12-hour rotating shift, there would need to be a minimum of 60 senior reactor operators and up to 120 reactor operators. This is only the minimum amount of licensed operators required to staff around-the-clock watch, and does not account for the time off or operator disqualification. Considering that licensed operators command a significant salary, this is a significant expense on the facility's O&M budget. For comparison, the typical 2-unit site producing roughly 2,000 megawatts typically has 30 to 40 senior reactor operators and 25 to 40 reactor operators. Of course, this can be addressed in interim on a case-by-case basis. However, case-by-case exemptions only serve to slow the approval process from the NRC. There is a worldwide demand for electricity-generating assets that are reliable, affordable, and environmentally friendly. Implementation of SMR technology can achieve all of these goals while adding to the betterment of a world where nearly 20% of the global population is without access to electricity. In countries such as France and Japan, integration of SMRs with existing power generation assets could allow these countries to balance their energy needs with their desire to reduce greenhouse gas emissions. In developing nations, SMRs can be a flexible and affordable solution to provide basic services to the population, while at the same time working within the capacity of small local electrical grids. SMRs are also well suited for inclusion in areas with large renewable energy assets. Such SMRs are better suited to these grids than their gigawatt-sized counterparts. Additionally, SMRs afford nations the ability to enjoy the benefits of carbon-free power generation without the fear of devastating nuclear disasters or proliferation. Now, prior to the accident in Fukushima, the nuclear industry was beginning to experience a renaissance of sorts, with new reactors being built in China, Dubai, and even the first nuclear construction in the U.S. in nearly 30 years. However, the events of March 2011 forever changed the world's concerns over nuclear power. In Germany, legislation that had overturned a planned phase-out of nuclear power was again overturned, and Germany announced that it would permanently retire its entire nuclear fleet by 2022. Germany currently plans to replace the lost generation with coal and gas-fired plants, while focusing on further developing its renewable energy base. Of course, this type of policy comes with a steep price. This plan will initially leave Germany largely reliant on other nations for its energy needs and an overall degradation of energy self-reliance. Furthermore, it is estimated that Germany would need to import 25,000 megawatts in order to compensate for the loss of electrical generation and still comply with the Kyoto Protocol. Despite this, a 2012 poll showed there is virtually no support for nuclear power in Germany, with 73% of those polled in agreement with the plan to scuttle the German nuclear fleet by 2022. France, on the other hand, would be an ideal nation to implement small modular reactors. As it stands, France currently gets 75% of its electricity from nuclear power, and electricity is the nation's fourth largest export. With such a large portion of its electrical needs coming from nuclear power, France is unique in that it employs its nuclear fleet in a load-following sense, meaning that as demand lowers, some plants are forced to lower their electrical output in order to maintain grid stability. Due to the fact that reactors have behaved differently at various times in core life, this requires a large amount of coordination between the various plants and their operating and refueling cycles. Although France is heavily reliant on nuclear power, as of October 2014, it has legislatively capped its nuclear generating capacity at 63.2 gigawatts. In order to comply with this legislation, France will have to shut down approximately 1,650 megawatts of nuclear capacity in order to accommodate the new Flamanville power plant, which is scheduled to begin commercial operation in 2017. Going forward, as France's aging fleet is retired, it is possible to replace the existing plants with SMRs. This would allow France to continue to reap the benefits of nuclear power and utilize its plants in a load-following configuration. Of course, no industrialized nation that currently uses nuclear power could benefit from utilization of SMRs more than Japan. Despite its experience with the worst that nuclear power has to offer, there are several factors that could contribute to large implementation of SMR technology. The smaller source term and passive safety systems present in SMRs should be of great interest to Japanese utility companies. A power facility with nearly the same generating capacity as some of Japan's older reactors can be built with several small reactors instead of one large one. This is beneficial in that each of the small reactors contains a small inventory of radioactive materials, thus limiting the potential damage in the event of a nuclear accident. In fact, NuScale claims to have a core damage frequency of approximately 10 to the minus 8 per module year, compared to a CDF of 2 times 10 to the minus 5th for U.S. plants as of 2008. This is attributed to the modular nature of the SMR as well as to its advanced passive safety systems that are capable of removing nuclear decay heat for extended periods of time without operator action or electric power availability. Another aspect unique to Japan that makes it an ideal candidate for SMRs is that the electrical grid in Japan actually runs on 2 different frequencies. The electrical grid in eastern Japan runs at 50 Hz, while western Japan runs at 60 Hz. The limitations associated with the electrical grid being run at 2 different frequencies contributes to difficulties in the efficient dispatching of electrical power throughout Japan. SMRs can help to alleviate some of this problem due to greater flexibility and incremental capacity generation. As older plants are retired, they can be incrementally replaced with SMRs, which would allow Japan to integrate their electrical grids over time. While there are numerous benefits to industrialized nations using SMR technology, developing nations stand to see the most gains. Many developing nations lack the financial resources or robust electric grid to build traditional full-scale gigawatt-sized nuclear power plants. In order to ensure grid stability, the general thumb rule is that the unit size of power plant should not exceed 10% of the overall electricity system capacity. Using this thumb rule, an electric grid would need to have roughly 12,000 megawatts of generation capacity in order to fully accommodate a typical full-scale 1,200 megawatt nuclear power plant. This is beyond the capability of many electric grids in non-connected rural areas or developing nations. A more feasible approach would be to implement a scalable SMR and add modular units as the needs of the population rise and the electrical grid becomes more robust. This would allow developing nations to not only benefit from cheap and reliable nuclear power, but also provide for energy independence and to lower the reliance on carbon-producing fossil fuels. In addition to being better suited to less robust electrical grids, SMRs provide a developing nation access to affordable nuclear power. Previously, investment in a full-scale nuclear power plant represented an all-in proposition for most companies, as overnight costs put plants in the price range of $5 to $10 billion. This is a staggering sum for most utility companies and developing nations. A small modular reactor costing $1 billion or less is far more practical for most interested parties, and it affords its owners the opportunity to pay as they go. Small modular reactor operators can begin to realize the profitability of the initial SMR while paying for the next. This is a key concept for developing nations, as the international pressure from industrialized nations to reduce greenhouse gases negatively impacts the developing nation. Other more forward-thinking uses for SMRs involves the use of nuclear power for uses outside of their traditional role as solely base load electricity generation. This includes the use of nuclear heat for desalination, uses in the recovery of crude oil, and in hybrid systems where some nuclear power is used for the generation of electricity and some is used for hydrogen generation. These diverse types of applications offer tremendous opportunity that has never before been explored with the more traditional large-scale plants. If utilized in this manner, SMRs have the capability to truly transform electrical grids into smart grids, as power from one reactor can be diverted to systems where it is needed. To support our arguments and our overall evaluation of pressurized light-water small modular reactors, we have discussed basic operations, major differences in design, global experience, safety characteristics, material proliferation, advantages, disadvantages, and the economic feasibility of this technology. To conclude, after carefully evaluating pressurized light water small modular reactors for their overall design, advantages and disadvantages, and global market effect, we had decided this option provides the safest, most economically attractive and flexible option, and the most environmentally friendly technology, giving us just the right fit for meeting the globe's enormous energy needs. Once again, my name is Christopher Haney, and I thank you for taking the time to watch my presentation on this exciting emerging nuclear option.